Hello everybody, welcome back today. Today we're going to be going over lowest common ancestor in a binary tree. And this is like a classic LeetCode question that's asked at almost every big tech company. So let's get into it. Let's go to the iPad for the explanation for this question. So what the least common ancestor is that it gives us two nodes here denoted by P and Q. And it wants us to find the least common ancestor among them. So what does that mean, right? Well, in this case, let's just find out where our P and Q are. So for example, in the first input, P is 5 and Q is 1. Or sorry, vice versa. P is 1 and Q is 5, right? So we want to find the node that is the commonly descended from. So what I mean by that is like which node are these two parents descended from, like from the previous parents, right? In this case, it's 3, right? Because 3 is the one that they're both descended from directly, as we see, right? And in the other example where it's given 1 and or where it's given 5 and 4, right? What are these two? What's the last node that they're descended from? Well, it's actually 5 itself, right? Because the 5 is the parent of this subtree, and then 4 is part of the subtree. So the last the last node that these two are descended from is actually 5, right? So if we think about it that way, what is this actually doing? Another way to think about this is like, let's just draw a path. Let's just start from the root node and draw a path from 3 to 5. That's my path, right? Now I'm going to draw a path from 3 to 5, right? Just 3 to 5 itself. So you see that they both have a commonality where it's actually meeting at 5, right? So that's actually going to be our LCA always, right? This is always going to be the LCA, where the path intersects. Same thing, if I were to erase this and I drew the paths from 3 to 5 and 3 to 1, you see that the commonality between these two paths is always 3, right? So that's why that's our LCA. So wherever the commonality occurs for the paths, then that's our answer. So maybe we can just do that. Maybe we can just generate the paths. Maybe we generate the paths in 2 vectors, right? 2 vectors, because using C++, but basically array lists or whatever like that. We generate those 2 vectors and we just find the common element. So the common element in these vectors is our LCA, right? Is the LCA. But the thing is, like, you can already see this is going to take a space complexity of O of n, right? And maybe we don't need that, in the sense that we don't want to have external like vectors here. So maybe we can just do it recursively, which will just take auxiliary stack space, right? So let's think about that. Let's think of a recursive approach. So first things first, maybe we can think about like how we usually do it. We would usually find a path by just searching for these nodes, right? We would usually try to find the path from 3 to 5, 3 to 1, or 3 to 4, right? So maybe we can do that. So what would that code actually look like, right? It would be something like this, like if root was like null, right? Or like the root value was equal to like p's value, right? Same thing, or root was equal to q's value, right? And here we're basically saying where are we going to find the first element where it's either equal to the q's value or the p's value, right? That's the case, we usually just return the root, right? So either it's actually null or it's actually, p or q, like the node itself, right? So that we do that, and then we always move left, right? So let's just say my method's called LCA, for example. We always move left, we always move right. So we do both of these, right? But since this method's actually going to return a node, right? We can actually capture these nodes, and this is actually useful here. So why is this actually useful? Well, let's capture these nodes, right? Now, what does LCA mean? So if we think about when we're backtracking, right? When we backtrack, then like we know that like whenever node where we backtrack to, and if those two nodes actually meet, like let's say left and right are not null, then that root node is actually going to be the LCA. Now let me explain why. So let's just say this, right? Let's say we were doing 5 and 1, right? So when we do a recursive call, we go left, right? And then we check, hey, 5 is actually now equal to the q's value. So I return, so I move back. I'm back at 3. And now this line gets run because the left has returned, right? And then so I go to my right. Hey, now I'm actually equal to my p's value. So I return my root again. I pop right back, and then my right's there. So now if my right, so here the left one actually is going to return 5, and the right one's going to return 1. Now, if those two returns, like the nodes here, if they're not null, then we know this is our LCA, which is true, right? 3 is our LCA. However, let's look at this other case. What if here we go to 5, right? And we see, hey, we're actually going to be equal to the p's value, which is our second input. Then we return. And then we go to our right. We go to our right, we go to 1. That's not equal to p or q. Then we go to our left, and then we hit null, so we return backwards, right, with a null pointer. We go right. Again, we don't see it, so we go back null pointer, and then we return back null pointer. We see the left side returned a 5, but the right side returned a null pointer. What is our answer? Well, we know it's 5, right? But why does that work? Well, the reason that this one works is because if they're not on separate subtrees, well, that means that one of the P or Q has to be the LCA, because then otherwise it doesn't make sense, right? Otherwise we won't have. Otherwise we will find an LCA, right? So that's why in this case, if whichever one is not null, we return that one. If they're both null, then we return that, because that means there's no LCA, right? So basically here we do a check. We check if left is equal to null. If that is the case, then we just return right, right? And then same thing, else if right is equal to null, right? If this one's equal to null, then we just return our left, right? Because we basically want to return the other one that's not null, right? Else, we know that case where like they're both not null, then the root, actually the one that we actually meet back after we backtrack, is actually the LCA. And yeah, you could kind of dry run more on this, but you can see how like when you backtrack and you hit the same point, then you can kind of tell that's the LCA. If you don't hit the same point, but like you have one side that's giving you an answer and the other side isn't, that means that one side, whatever the answer was returned, that was the last element to be found, right? Like that was the initially from the top, that was the first one. That has to be this least common ancestor, right? So that kind of makes sense. So let's get into the code and let's see what we're talking about here. All right, so let's get into the code here. So again, lowest common ancestor of a binary tree, and I'm going to be doing this in C++, but again, you could do this in any language. The concepts do transfer over. So first things first, we want to write our base case, right, since we're doing recursion. And our base case is going to be, like we said, root can be if root is equal to null pointer, or if the root's val is equal to p's val, or if the root's value is equal to the q's value, right? So if this is the case, then we actually just return this root. And that's because like if the root is null pointer, this will be a null pointer. If the root is actually equal to any of these values, we're going to return the respective P or Q node, which is what we want, right? Because again, we're going to go left and then we're going to go right, and then we're going to see if we can capture any of these nodes, basically find them on the path, right? So here I'm going to have the left, right? And this is basically the thing I'm going to capture when I go left, right? So root left, and then I'm just going to pass in the parameters P and Q. Same thing, I'm just going to copy this statement because we're just going to essentially just change it to the right. And remember to change it here. This is the main point where we want to change it. So now basically we're going to capture whatever a node that we find from the left, whatever node we find from the right. And if any of these are null pointer, we want to return the other one, right? So if left is null pointer, we want to return right, because the case is like, this is how it kind of goes. Like there's three cases kind of. So basically like if none of these are null, that means whatever point we hit back at when we're backtracking. So like after this point, when we get here, right, we're actually backtracking, right? Because we're going back in the recursive calls, we're going back forward up the stack. So if none of these are null, whatever point we meet is actually going to be the least common ancestor, because that's where basically the nodes, basically these two nodes, P and Q, that's where they actually descended from. So that's how we know it's going to work. If any of these are null, right, then we know like basically like we found the highest up node on the tree. So like the one that's closest to the root. And that's the case, that must be the least common ancestor, because we're just assuming that since we're known, basically LeetCode tells us, like, it tells us P and Q will exist. Since we found one of them and we can't find the other one on the other side, we know that one must be it, because that must be the subtree where that other node, right, must descend from. So that's how we know that actually works. So here I'm going to do that checking, right? If null pointer, right, left is null pointer, we just want to return the other one, which is right. Else if right is null pointer, in this case, that means left cannot be a null pointer, right? Otherwise, it would have gone through the first if statement. So then here we just return left, right? Else, we're just going to return root. And this is the case where like left and right are both not null pointer. So let's just run this, make sure that we pass these three cases that they have. And we do. Let's just submit it, make sure we pass all the LeetCode test cases that they have. And as we wait, because LeetCode wants you to pay premium to speed it up. But yeah, as you see, we pass all the cases. So let me know in the comment section down below, and if you had any questions or any confusions about the explanation that I gave you. But yeah, make sure to like this video, subscribe to the channel, and I hope to see you on the next one.